Welcome to Chapter 19. This is Carboxylic acids and nitriles. This will also have some review from the previous chapters as we have been discussing the mechanism under which carboxylic acids derivatives undergo, and that is nucleophilic, acyl substitution reactions. And that is the mechanism in which you need to be able to draw. Okay, so here's a functional group transformation. This is an alkene, and you're trying to do a synthesis, so you're trying to fill in the starting material and the missing reagents. So how could you make an alkene? And you look at, you're adding a carbon here. So you know to make alkenes, from previous chapters, they're usually E1 or E2, and there's also the Vidic. And so we've been doing carbonyls and Vidics. The starting material for a carbonyl would be, or for the Vidic, would be a carbonyl, an aldehyde, or ketone. So would you think the starting material would be an aldehyde or a ketone? So you see you have the carbon there. So ketone would be the starting material here. And so that's these carbons here. And then this carbon for the other part of the Vidic would be this one right here. And notice I put the double bond between the phosphorus and the carbon. And so those reagents are 2 and 6. Do we have 2 and 6? I don't see 2 and 6, so you can just fill it in. I think this was meant to be 6 here. All right, so acid catalyzed hydration. So this is what you're going to be having to do for some of these. Most of these, this is review still, ketone or aldehyde. How do I know that? It's because this R group is either a hydrogen or alkyl group. And I think we're still talking about the amine review. So this gets protonated. That's first step because you got to activate. This is obviously, they're adding a water to the carbonyl. I've been focusing on more like an alcohol, methanol. This is a weak nucleophile. So in weak nucleophiles, you need an acid catalyst to do this first step of protonation of the carbonyl oxygen. And this makes the carbon of the carbonyl oxygen more electrophilic. And then, of course, your nucleophile that's weak can come in and form a carbon-oxygen bond here, and then you deprotonate. Like I said, we're not focused on the hydration as much as making a hemiacetal and an acetal. So you need to know that. So this is review of that acetals. More details in the previous lecture. Here, you can't sometimes control how many equivalents you're going to have because usually your methanol is kind of your solvent. But here you're going to have, this is a weak nucleophile. You're going to get protonation of the carbonyl. So you want to get used to doing that as your first step. And then your weak nucleophile then with its lone pairs can come in and attack that. And it'll do this 2 times. And so when this does it 2 times, you'll form an acetal. A specific acid that is often used is tosic acid. Tosic acid is para-toluene sulfonic acid, where this is the acidic proton. It's a soluble in organic solvents, and this is showing you that this is an acetal, which is a new functional group. This is a way to protect ketones and aldehydes. And we've talked about protecting groups. That kind of just mask that functional group so you can do other functional group transformations on other parts of the molecule. So this is showing you the ketone, ethylene glycol, tosic acid makes a cyclic acetal. We've talked about this in previous slides. lectures. This is the mechanism, so review that. Here's another detailed mechanism that you can review. And then this is showing you that you can deprotect. So deprotect is what you can do here when you have an acetal. So you see you have an acetal and you add water and acid, so just H3O plus and water, you can get back your ketone. And then of course you get the ethylene glycol. You do not have to draw this mechanism going back to the ketone. But I do expect you to be able to take the ketone to the acetal. I expect you to be able to do that. Okay, so as you see here, this is your acetal. So you need to recognize that that's a new functional group. The carbon is bonded to 2 oxygen. And then the question is this so this is an carbonyl. Is it an aldehyde or a ketone? Well, you know that that carbon is bonded to 4 things, 1, 2, 3. So what's not shown is a hydrogen. So that should help you to know that that is an aldehyde. And so this is the aldehyde, and you're adding oxygen. And there's your oxygen, and then because you're adding water. So the other are going to get you can just, the blue oxygens here, the alcohol is going to get the 2 hydrogens. Okay, so you added water across that molecule to do the hydrolysis. Hydrolysis, where water splits that to the acetal and the ethylene glycol. So this is obviously your aldehyde of your starting material. You need the correct alcohol with acid. So this would be 7 and 4. So D is the answer. Okay, so these are acetals as protecting groups. This is a slide that we went on the previous. You have an ester, and then you have a ketone. The ketone is more reactive. So if you want to do reduction of an ester, which you know to do lithium aluminum hydride would be that reagent here, you would have to protect the ketone. Otherwise, you're going to get reduction of the ketone to the secondary alcohol. So to do that, then you can first add acid. It can be para-toluene sulfonic acid or just H3O plus, and then some kind of alcohol. A lot of times we just do the ethylene glycol. That would protect this ketone as a ketal. Make sure you have 6 carbons, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this would give you this compound with 1, and then you can add lithium aluminum hydride, and then that's going to reduce your ester, this is an ester, to the primary alcohol. Count your carbons, 1, 2, 3, 4, 5, 6, and then you can add the acid and water to get you the desired ketone, hydroxyketone. And that's what you're seeing here. Step 1 is protection as the acetal. Step 2 is reduction of the ester to the primary alcohol. This is a strong reducing agent. And then deprotection of the acetal back to the ketone. And this is the strategy in which you need to use protecting group. So also you can have an intramolecular acetals. These are hemiacetals. And so whereas this is the hemiacetal. This came from, so you have 3, so that came from an aldehyde. And then you count your carbons, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So that is a hydroxy aldehyde. This one right here 1, 2, 3, so it has a hydrogen there. So that's a aldehyde, and then that's 1, 2, 3, 4. 1, 2, 3, 4. This is where your OH comes from. So this is that oxygen here. This is that oxygen here. And so you can see that these hydroxyaldehydes are not found in nature as the straight chain. They're going to be 94% found as the hemiacetal. And it'll be a cyclic. And the reason why this is important is because this is what you're dealing with your sugars and your nucleotides in biological systems. And this is just showing you the intramolecular attack. Acid protonates the carbonyl oxygen to make it the carbon more electrophilic, and then you have this intramolecular attack. Whenever you make 5 or 6 membered rings, this will happen because it's energetically favored. As you can see, this is a 6-membered hemiacetal. And also, because this sp2 carbon is being attacked from the top and the bottom, you're going to get a new stereogenic center, and we just draw it because it's going to be racemic, meaning you're going to get 50% of one enantiomer and 50% of the other. You can just show this by the straight line. What's nice about hemiacetals, you can go ahead and react it with methanol and acid to make the acetal. And this is the mechanism. This is the second part of the big mechanism that I expect you to know, where you protonate the hemiacetal OH to make it a good leading group. Okay, so now it becomes water, so it protonates. And then what I like to see is these electrons do a push, and you can go straight to this, where you reform the carbonyl. And then your nucleophile here will attack the carbonyl to give you this compound, and then deprotonate, remove that last proton, to give you the acetal. And this is the second part of that mechanism. Cyclic hemiacetals are formed. So here, what they're trying to show you, this is a hemiacetal. So it will go ahead and react to the acetal. This is just a regular secondary alcohol. So there's no reaction here. So look for that. Even though they look similar, you got to look at this carbon and see that it's bonded to 2 oxygens. So it's a different functional. Where we see that is in our carbohydrates. This carbon here, a lot of times it's called the anomeric carbon if you take biochemistry, and you'll see that that anomeric carbon is bonded to 2 oxygens. That's a hemiacetal. So you can do chemistry. You see that that makes bonds to another sugar. So this is a disaccharide, and this is called a glycosidic bond. And that's different than all the other OHs here. These are just regular secondary alcohols. Glucose has all their OHs in the equatorial position. This is a primary alcohol, so it's going to react a little bit different. It'll react faster than like the secondary alcohols. So you see that these are secondary alcohols, but this is a hemiacetal. Do you see that this is an acetal? So when it's in a disaccharide glycosidic linkage, a lot of times this would be, so this would be beta because it's going up instead of down. Beta, and that's carbon number 1, because the anomeric carbon gets the number 1, and then you go around the ring, 2, 3, 4. And then, so this would be 1, 2, 3, 4. This is named 1,4 glycosidic bond linkage. So how does this happen? Well, sugars will spend about 1% of their time in this open chain, but this is it's the closed chain. It's called the Haworth projection. You studied this. This is the hemiacetal, and this is 99%. It's going to be in this cyclic form of the hemiacetal, and this is the way that the sugar travels in the blood. So you know glucose is in the blood, and it's going to be in the Haworth projection. You see it'll probably be the beta D glucose. All right, so that was review. Let's go on to chapter 19, carboxylic acid derivatives. You do have a POGL on this. So this is a carboxylic acid. You see it has a carbonyl, but then it has an oxygen. And then the question is, what is on the other side of the oxygen? Oxygen gets 2 bonds. If it's a hydrogen, it's carboxylic acid. So this is the carboxyl, you'll see, which is different. Carbonyl group is the carbon double bond oxygen. So some different carbonyl kind of compounds is aldehydes and ketones. So they have a carbonyl. But carboxylic acid derivatives have a carboxyl. So, and that's if you have the extra oxygen. Now, depending on what's bonded to that other oxygen depends on what its functional group will be. So we want to know what the derivatives of carboxylic acid are. This is sp2 carbon. This is acetic acid, which is the active ingredient in vinegar. And they're just showing you some bond angles and bond lengths. It's a very polar compound. They do hydrogen bonding. They actually do 2 hydrogen bondings. They're going to have very high boiling points and melting points. Now, cyano group is kind of like a masked carboxyl. So you know that you can do sodium cyanide and do some SN2 reactions. So if you look at the Lewis structure for that, that's a strong nucleophile. Okay, because sodium is a positive electrostatic interaction. But what's nice is you can add acid and heat, kind of water and heat, and you can convert the nitrile group to a carboxylic acid. And this is sp hybridized, and nucleophiles will attack at that delta positive carbon. This is just showing the intermolecular forces. You have double hydrogen bonding here, forms a dimer. And therefore it has very high boiling points. You see 118 versus an alcohol that just has 1 hydrogen bonding and has 97 degrees. So a lot of this is acetic acid, which is a liquid, but you can get into some solids at room temperature pretty quickly. Aldehydes have just dipole-dipole, and then the alkane has van der Waals as their predominant intermolecular forces. All right, so here is a slide. This is reviewing a protecting group chemistry. You see you have an aldehyde and an aldehyde. Aldehydes are very reactive. So how do you get a ketone functional group transformation to a secondary alcohol in the presence of an aldehyde? Well, you're going to have to do some protecting group chemistry. So the first thing you want to do is you want to mask the aldehyde. And you can do that because the aldehyde is going to be more reactive. So you can, I like the intramolecular cyclic protecting group. So that would be this one here. And then you can go ahead, this is a reduction. So you need a reducing reagent. You can use a mild one. I would use a mild one. So you can just do a methanol. And then that's going to give you, that's step 2. And when you do these multi-step syntheses, I do recommend you do 1 step at a time, draw your product for that one, and then the next one. So then to go to the product here, you're going to have to hydrolyze this acetal. This is now an acetal. You formed an acetal, and that's acid and water. So where do we have acid and water? Number 1. So then we can go find, here we have 4, then we have 5, and then we have 1. So B is your answer. Okay, so some carboxylic acids that you may be aware of that you don't know you're aware of is formic acid. Formic acid has a hydrogen, so this is the carboxylic acid, where hydrogen is attached to the carbon. It's the smallest carboxylic acid, and it's the sting, like if an ant bites you. It's a common name, old school. Acetic acid is that bad acidic taste that you get from vinegar. And so this is a CH3. So a lot of times you'll call this the acetal, and then so that's acetic acid. Hexanoic acid. Now we're getting into the more of the IUPAC names. This would be 1, 2, 3, 4, 5, 6. So that's hexane. You're going to drop the E and add oic acid. So this is hexanoic acid. You don't have to know any of these common names. Oxalic acid has like this carboxylic acid here and carboxylic acid there. Lactic acid is the buildup when you do some sprinting and your legs get really tight and the muscles get tight. You're feeling the lactic acid built up. So this is a carboxylic acid. It has 3 carbons, but it has a secondary alcohol on its alpha carbon. Sodium benzoate, so this is the benzoyl group here. This is potassium, so you say potassium, and this is sorbate, but that's a common name. Where do we have, this is a nitrile. Remember, nitriles are kind of like masked carboxylic acids. So where do you find the cyano? Lexapro. And this is another Calan drug. Aspirin has carboxylic acid, so here's the carboxylic acid in aspirin. This is an ester over here. This is a benzyl alcohol, benzylic alcohol. This is right here. Why is this showing you this? This is 1, 2, 3. That would be 1, 2, 3, a hydrogen. So this is an alcohol here, and that would, here we have another carboxylic acid, but they're just showing you that it's got a sugar added on. And that's kind of interesting because that's an acetal from the willow bark. And this is sodium salicylate, and it's kind of sweet. All right, so how do we make, how when we start a new chapter, how do we synthesize that new functional group? So that's always what we do. So what are reactions that can make carboxylic acids? Well, you can oxidize, oxidation of primary alcohols using the Jones reagent. Primary alcohols will go to the carboxylic acid. You can oxidize aldehydes with the Jones reagent here, same thing, carboxylic acids. Remember that only primary alcohols can go to aldehydes and then carboxylic acids. Secondary alcohols go to ketones. Tertiary alcohols do not oxidize. Okay, I didn't really go into this, but you can do Grignard with carbon dioxide. I'm not too worried about that one. This one you do need to know. Permanganate will do benzylic oxidation, and we've talked about that. And then oxidation of alkynes, this is ozonolysis. So you see ozonolysis, the terminal alkyne will go to CO2. And if it's an internal alkyne, they just go to 2 carboxylic acids. Okay, what's the missing reagent here? You see that this carbon, this benzylic carbon, did not change. Okay, that's because there's no hydrogens on that carbon. No hydrogens on this benzylic carbon. This one does, so this one is oxidizable, and it oxidizes to the carboxylic acid. You need to know that potassium permanganate is the reagent of choice for benzylic oxidation. And benzylic oxidation takes that primary carbon and will oxidize it to the carboxylic acid. All right, so carboxylic acids are the organic acids. They have an acidic proton. I expect you to know that. So when you react it with a base, the pKa is about 5. And so that proton, so these bases, it doesn't even have to be a strong base, will deprotonate. That's the first thing that will happen because protons are small and easy to deprotonate compared to nucleophilic addition. And you get a carboxylic acid anion. And then, of course, the pKa of the conjugate base will determine how far this equilibrium is to the right or the left. So here's an example. Like I said, it's about 5. And sodium hydroxide, which is a pretty strong base, that gets you about 16. So 5 and 16, what's 16 minus 5? 11. So you have 11 zeros times. So that is not the right way to do that arrow. Here, sodium bicarbonate, this is a weak base, and you get a weak acid. That's a weak acid, carbonic acid. Where have you seen carbonic acid? That is your blood pH buffer. So you're looking at 6.2 and 4.2. You're looking at 100 times to the right. So this is just showing you some bases and then their pKa's of you don't need something really strong to deprotonate carboxylic acid. All right, so when it gets deprotonated, the reason why this hydrogen is an acidic proton, you remember there's 4 factors that determine whether a compound, a hydrogen, is going to be acidic or not, and more acidic than others. Resonance is one of the 4 factors. And you see when you deprotonate that and you make your conjugate base, it is stabilized by resonance. All right, so they're just showing you that acidic protons are about a pKa of 5. Phenol is a pKa of 10, which is also resonance. And alcohols are 16. And so this is an element effect here because when you deprotonate the hydrogen, the conjugate base, the negative charge is stabilized on a more electronegative element such as oxygen. So ethanol pKa is going to be around 16. Compare this to something like hydrogen. What's the pKa? Or something like that, an anion. Well, you know that pKa of an sp3 carbon hydrogen bond is about 50. So that just shows you element effect does factor into making that proton more acidic. The big difference between 16 and 50. This is organic 1. This pKa is 10, and the reason why is because the negative charge can be stabilized on the carbon within the ring. And that's just showing you those the stability. Now here the carboxylic acid though it's resonance stabilized, and therefore it is going to be the lowest pKa value. And that negative charge is stabilized on the oxygen. So the other one's resonance for phenol, but you're stabilizing the negative charge on the carbons. So if you're wondering why is a phenol pKa that undergoes resonance, well, why is that so much or not as much? So that one has resonance, right? But also a carboxylic acid has resonance. But when you do your resonance structures, you see that the negative charge is stabilized on the other oxygen. So that's going to be an element effect with resonance there, as comparing those two. All right, another thing, this is inductive effect, okay? So of the 4, inductive effect will also have an effect. So this is just regular acetic acid where this carbon has hydrogens here, pKa about 5. If you have electron donating groups, the pKa is going to be less acidic. But if you have electron withdrawing groups, and this is pooling the electron density through the sigma bond, that's important for reductive. That's different than element effect, okay? So even though this is more electronegative, it's pulling it through the sigma bond, which makes it an inductive effect. The more, and usually you get about 3 bonds. After 3 bonds away from the negative charge, so here's the negative charge, you have 1 bond, you have 2 bond, you have 3 bond from the negative charge. So this electronegative element, Cl, is stabilizing that negative charge. The more electronegative elements you have on this carbon-3, the more stabilizing of the conjugate base it will be. So this is what this is demonstrating here. Here we have 3 electronegative chlorines that are 3 bonds away. 1, 2, 3. And so that has a pKa of 0.9. This one only has 2. This one has 1. So, and fluorine is even more. Look at 1 fluorine, you get a 2.6. So, because fluorine is more electronegative than chlorine. So even though you're comparing electronegativity, this is an inductive effect because it is stabilizing through this sigma bond. Once you get this many bonds out, you don't see. So there's 1, 2. This is your alpha carbon here. This is your beta carbon. And here's your alpha carbon. So you see the effect more on an alpha carbon, the closer withdrawing group. And this is because it's an inductive. Okay, and this is showing you more. You can have electron donating groups versus electron withdrawing groups. If you have the negative charge, an electron donating group is going to destabilize the conjugate base, okay, because it's pushing electrons towards, which is making that more negative. Electron withdrawing groups will stabilize the negative charge. And so electron withdrawing groups is going to make this benzoic acid even more acidic. And so you know these activating groups, these are electron donating groups, but these electron withdrawing groups are the ones that are going to make the benzoic acid more acidic. Okay, so sometimes you have to pick out the most acidic proton, and so you need to look at molecules like this, and this HA is an aldehyde proton. This is not acidic, not acidic. Okay, do not go for that one. This is a phenol proton. So the pKa of that is about 10. This is a carboxylic acid proton. pKa is about 5. This is a carboxylic acid proton. pKa about 5. So we got to compare the 5s here. Which one's going to be more acidic? Well, here's your alpha carbon. It has chlorine. This alpha carbon has 2 fluorine. Fluorine's more electronegative, so the inductive effect is going to make this probably 100 times more acidic than this one here. So I would choose HD. Okay, so here we have benzoic acid is right here. This is benzoic acid. And remember, this is an electron donating group, so this is going to be less acidic than benzoic acid. So benzoic acid's here, and then that's going to be more acidic than number 2. The least acidic compound, well, that's going to be 2. These are going to be the most. You got a nitro group, which is more electro withdrawing because it has a full positive charge. So that was going to probably be your most. We could look up pKa's for these compounds to just justify our answers. And then 1's going to be the second. But it wants the least acidic, so it's definitely going to be 2 because this is an electron donating group. All right, so remember I said nitriles are like masked carboxylic acids. In this chapter, the reactions are carboxylic acid derivatives. And you have already been taught the mechanisms. So a lot of this is just going to be going through some reactions and reagents. So you know this reaction, sodium cyanide does an SN2 reaction. And now that's how we can get the nitrile on the carbon-carbon chain. Okay, so here we have 1, 2, 3, 4. 1, 2, 3, 4, we just made a 5th carbon. Okay, so it also does homologation. Homologation is when you increase the numbers of carbons in the chain. Okay, it's called a homologation. Now, this is also a delta positive, so this is an electrophile, and nucleophiles can attack there. And so here we have this nitrile. And so if we add water and acid, and you don't actually have to go through a lot of these reactions because there's a lot of protonation and deprotonation, and I'm just making you do that for acetal, so you don't really have to go through these mechanisms. But you do need to know the organic functional group transformations. So here, water and acid are going to make the carboxylic acid. If you have it in base, it's going to deprotonate. So that's all that is. Lithium aluminum hydride will make the amine. This is important. Dibyl H is mild and will stop at the aldehyde, okay? And then your Grignards will add to a nitrile to make a ketone. And so this is showing you carboxylic acid. So if you have some nitrile and acid and heat, you can convert that carbonyl to a carboxylic acid. So it's this is reduction, and so this carbon of the nitrile is going to go, and it's going to still keep the nitrogen, but you're going to add hydrogens onto the carbon and hydrogens onto the nitrogen. And this is going to make an amine, and this is a primary amine. It'll make a primary amine. If you want something milder, it will make the aldehyde. So you'll actually lose the nitrogen. And because you have water, you're going to form an aldehyde for your functional group. Like I said, you don't have to know the mechanism, but you do need to know, okay, so we have a nitrile here. So this is that carbon, and it's a carboxylic acid. So we went from a nitrile to carboxylic acid. So what's that functional group transformation? Nitrile to carboxylic acid, you need acid and water. All right, I guess we're starting chapter 20 on this, and then I was going to make another lecture for chapter 20. So this might be combined. Let's see. This is carboxylic acid derivatives. All right, so you do have a POGIL exercise that does carboxylic acid derivatives. A carboxylic acid derivative, you need to look at what's bonded to the carbon of the carboxyl group. If it's Cl, it's acid chloride. If it's another carbonyl group, it's called an anhydride. So if it's an OR, it's an ester. If it's an NH2, it's an amide. So we have, these are anhydrides. You don't have to name them, but you do need to be able to recognize their functional groups. This is an amide, and it's a primary because the nitrogen has 1 carbon bond. This has 2 carbon bonds on this nitrogen, so it's a secondary amide. If the nitrogen is bonded to 3 carbons, it's a tertiary amide. Okay, stability of carboxylic acid derivatives. Amides are going to be like solids at room temperature. They're going to have higher boiling points and melting points than carboxylic acids. They are the highest, and they're the least reactive. They're the least reactive. That's important because our peptides, which make up our proteins and amino acids, are amides, and we want them to be very stable. Okay, so they're like rocks. I mean, they are not reactive. Esters are pretty reactive. I would put esters above carboxylic acids. Acid chlorides are the most, okay? They are the most reactive, and then anhydrides second. And then I would do esters are third. I would do carboxylic acids are fourth, amides are least. I would even consider these very non-reactive. This is important because we're going to be converting the carboxylic acid derivatives. So here, the mechanism, which you've already been taught, nucleophilic acyl substitution, you have a leaving group, and the nucleophile will come in, make a tetrahedral intermediate, and then you're going to get reformation of the carbonyl where the Z is the relieving group to reform your carbonyl. That is very energetically favorable, and you're going to have a new nucleophile compound attached to that carbon. So you can convert carboxylic acids into other carboxylic acid derivatives. And the derivatives are what we just went over, the functional groups. So we just went over the anhydrides, acid chlorides, amides, esters. And so this is what it's showing you. The nucleophile adds to the carbonyl, forms a tetrahedral intermediate. This tetrahedral intermediate reforms the carbonyl for the leaving group. And that's how you get a new carboxylic acid derivative. Which kind of nucleophiles will participate in this? OH, which is going to make, so if that'll make a carboxylic acid. OR is going to make an ester. Any of these nitrogens are going to make amides. Okay, so these are the functional groups in which these will be made. If you have this carboxylic acid that is your nucleophile, this is going to make an anhydride. All right, so the other thing, acid, I told you acid chlorides are your most reactive. So they can convert to all derivatives. So you can take, this is very important, an acid chloride can go to all derivatives. So what are they? They can go to a carboxylic acid. They can go to an ester. It can convert to an anhydride. And it can convert to an amide. So a lot of times, and how do you make an acid chloride? So how would you convert this? Carboxylic acid using thionyl chloride. So you can take any carboxylic acid and go to the acid chloride using thionyl chloride. And this is usually the path. And then once you get to the acid chloride, you can go to any derivative you want. So this is going to be the path you want. Carboxylic acid to acid chloride. And the way you do that is you just add thionyl chloride, SOCl2, and then you can go to all derivatives, all and any. So here's a carboxylic acid, and this is showing you how to make the ester. This is called Fischer esterification. It's an important reaction, and it requires a carboxylic acid, it requires an alcohol, and it requires an acid. So there's three things to make an ester. That's called Fischer esterification. You need acid as the catalyst, you need the alcohol, and you need a starting material, carboxylic acid. Now, this is important. When do you need, so when we did aldehydes and ketones, when did you need acid catalyst? Well, you needed the acid catalyst when you had a weak nucleophile, right? So we saw that with water, we saw that with alcohols and amines. That's when you needed the acid catalyst. If you had a strong nucleophile, you didn't need an acid catalyst. Well, carboxylic acid derivatives do not depend on the nucleophile. You need acid catalyst depending on the starting material functional group. Okay, so remember I said that these are acid chlorides are the most reactive. No need for acid catalyst. We don't need that. Acid anhydrides, no need. This is acid anhydride, or just an anhydride. These are very reactive. Okay, so they don't need acid catalyst. What does? This is going to need acid, an ester. They're not reactive enough. Carboxylic acids, they need acid catalyst, not reactive enough. Carboxylic acid. Amides definitely would need acid catalyst, not reactive. Okay, so these are the ones that are going to need your acid catalyst. These are similar. Esters are definitely, I would say, about 100 times more reactive than the acid. How do I know this? Because when I was working at Lilly, I would do a reaction. If it was too reactive of an acid chloride, I would immediately go to an acid anhydride. If the acid anhydride is still too reactive, I would go to an ester. So you can pick and choose the functional groups and kind of slow the reaction down in order to create an increase in yield to get a compound you need. Amides, I would look for different ways. Amides and carboxylic acids. I mean, you can go, basically the only carboxylic acid derivative you can go to with an amide is a carboxylic acid. It's going to take you weekends. It's going to take you the weekend. It's going to take refluxing, heat, and then you can get the carboxylic acid and go to the acid chloride with thionyl chloride, and then you can go to whatever you want. Okay, so it's all about the leaving group ability here and the reactivity of your carboxylic acid derivative. The nucleophile is going to form the tetrahedral intermediate, and you got two possible leaving groups, okay? So, and that's what usually slows the reaction down or makes some reactions more fast. So they're showing you that what kind of nucleophile would you want in order to make an acid anhydride. If this is your leaving group, you can just go ahead and make that acid chloride. If you use a carboxylic acid derivative, you'll get an anhydride. If you use like sodium hydroxide, you're going to get carboxylic acid. If you add an alcohol, you're going to get the ester. Keep in mind, yeah, none of these need acid catalyst if you have a Cl. If you use any kind of amine, you're going to get an An. What is the missing reagent here? Well, you went from a acid chloride to an ester. So this is a great leaving group. This is going to be your very reactive. So you don't need, no need for acid catalyst. So you don't need an acid catalyst. If you chose it, it would be wrong. And this is your methanol. So this is your alcohol that comes in, forms your tetrahedral intermediate. So that mechanism here. Tetrahedral, four things. There's your nucleophile. Make sure you get your positive charge. And then another methanol would actually deprotonate that. Or you could just go down and do this. I'm okay with that, the mechanism. Like I said, I don't like to do these mechanisms from the standpoint, I don't want you to spend a lot of time doing the deprotonation on these. But yeah, you could do either way. You could deprotonate and then do the step, or you could just do, I would be okay with you going straight from your tetrahedral intermediate to the Cl leaving. But then you would have to do a deprotonation step. Most important thing is that you recognize this is an acid chloride, this is an ester. Yes, you can go from acid chloride to an ester. You do not need acid catalyst, but you do need a methanol nucleophile. What is the missing reagent here? You have a carboxylic acid and an ester. So this is an ester from a carboxylic acid is Fischer esterification, and that requires three things. You need a carboxylic acid, you need an alcohol, and because it's a carboxylic acid, you're going to need an acid catalyst. And if you miss any of those things, it's wrong. So acid catalyst and your nucleophile, your alcohol is right here. So 3 only would do Fischer esterification. Now this one, what happens with the acid catalyst and the mechanism is the first thing that has to happen is protonation of the carbonyl, okay? You're not going to protonate the OH, okay? Not on this. A lot of people do that. No, that's acidic. So the first step is going to be protonation of the carbonyl oxygen, and then your alcohol here, CH3OH, can do a nucleophilic addition to make your tetrahedral intermediate. You got to have 4 things there. There's your O, CH3. Now at this point, deprotonation, whatever, I'm okay with you just reforming your carbonyl and having that as a leaving group. But this also gets, this has to get protonated. This is another reason why you have to have acid. And this is where you would deprotonate here and then protonate here, reform your carbonyl to get that, to make OH as your leaving group. Okay, why would, this is hard to do. You have to heat it. Okay, it's gotta be harsh. You have, because you'll see that this is not a bad leaving group either. So the way you do that is you don't have a lot of water and you limit the concentrations of things. But like I said, tetrahedral intermediate and then reform of the carbonyl with this protonated as the leaving group. Okay, that wraps up this portion of the lecture.